Okay, so today we'll start from this section 2.10 risk we addressing for wide immediates and addresses. But before starting today's lecture, there is a small announcement. By the end of today, I think tonight you will receive your first assignment on risk B. That is actually an ungraded assignment. I'll give you 4 or 5 days to practice these assignments, and also by tomorrow morning you will receive another email from head TA, and that email the TAs will be allocated to the students. So since you can there are 100 students, almost 100 students, so it is not possible to manage all the students by a single TA. So there are 5 6 TAs in this course. So the head TA will send a mail where the students will be assigned to a particular TA. So in the practice, during when you will practice those as the first assignment, at that time if you face any issue, you can contact the TA, and TA will solve your issue, and TA will try will help you. So and the next week, most probably 15th or 16th, you will receive your graded assignment, and you have to submit the graded assignment within 23rd. Okay, and yes, there will be two short quizzes in this week in tutorial session, because the short quizzes are pending. So since short quizzes are for very limited time, so in the next tutorial session is on Friday 6 p.m. So in on next tutorial session there will be two short quizzes, and the syllabus and all I'll mention in the Google Classroom after this class. Okay, so let us start today's discussion. We'll start from this section. So we'll start with white immediate operands. So the operands that we know till now, the immediate operand, suppose add I x9 x12 to 40. So here for this immediate we have only 12 bits, right? So with this 12 bits, the number of constant that we can use is very limited. So compared to this x9, x12, for example, x12 is of 64 bits, right? X12 is of 64 bits. And so what you are doing with this add instruction, you are adding the content of x12, which is of 64 bits, and with this you are adding the content of adding this constant, which is only 12 bits. So only 12 bits here will be 240, and remaining all bits here will be 000, suppose, or 111, so extension based on the number. So if it is positive or a negative number, so as it means that the constant that you can use with this type of instruction is very limited. It's limited only with 12 bits. Only 12 bits you can use to represent a constant. So what about if the constant is of larger size? So today we'll discuss a instruction here. Using this instruction, you can add a, instead of 12 bits, you can use 32 bits constant. 32-bit constant you can load to a particular register. So how you can load a 32-bit constant in a register? So that can be performed by this instruction lui, suppose x19. Okay, and then you need to write a constant here, suppose immediate value. So this value you can load. So the process is I need to explain here. So instead of writing a separate example, I'll use the example that is given in book. So what there is in loading a 32-bit constant. So how to load a 32-bit constant to a register using this lui instruction. So since it is a 32-bit instruction, so what we will do, let us remove this because this number they are showing here, it's a 64-bit constant. Let us concentrate on a 32-bit constant. So remaining thing is a 32-bit constant, right? So in 32 out of this 32-bit constant, so what this lui will do, lui will load this constant into a register. Suppose if I go for this instruction, then this lui instruction is loading the constant. Ignore the bit size now, just concentrate on the constant. So if this instruction is loading a constant in this register is called x19. So what is the length of this register? Every register, sorry, uh, every register in risk V is of 64 bits, right? So this is a 64-bit register. So out of this 64, let us divide this 64 into 32 bits. This is 32 bit, this is 32 bit, this side, right side, left side. Okay, so now what is concentrate on this line, it is a loading 32-bit constant. So using LUI, this instruction, we are loading a 32-bit constant. So what we will do, we'll load the constant in the right half of this register. So if this is the 64-bit register, we'll load the constant here in this side, and the left side will be filled with the leftmost bit. If the leftmost bit is 1, then all bits of this 32 left side will be 111. And if the leftmost bit of this right half is 0, then the all the 32 bits here will be filled with 0 0 0 0 0. Right? So only thing here is how to load the 32-bit constant in the right side of this register. So we'll here we're assuming x19. So now suppose this is the number I am showing here, and it is given in the book. And from this number, what I'm saying, that you ignore this first, the left 32 bits, will only concentrate on this 32-bit constant. So now what this LUI do, if we write this instruction, you can see the instruction. If I write here LUI x19 and 976, what is, why 976? So what LUI will do, uh, uh, from this let us just concentrate on the right side of this 32 bits. So in this right side, if I divide distribute these bits of right side, then there will be from 0 to 11, these are the bits, and from 12 to 31. Okay, so now this LUI, if I write here LUI 976, then these 976 will be loaded here, 976 here in this place, bit number 31 to 12. You have to understand this. This is a special instruction. If you write LUI x19 this, then these constant, that is 976, will be loaded in x19. But in which position? First, this is the x19 register. You divide it into 31 31, then you ignore the left side half, you ignore this. So now when you concentrate on right side, then the right side there are 32 bits. So this 32 bit will be divided into 0 to 11 suppose, and then from 12 to 31. So this 976 will be loaded in this 12 to 31 part. Okay, and these values will be 0 0 0 in binary. In suppose, so value is this 976 is I have written in decimal. Ultimately the value will be stored here in binary, right? So these values will be 0 0 0. And what about these values? These values will based on the lastmost bit here. If the lastmost bit here is leftmost bit is 0, then everything will be 0 0 0 0 0 here. So this is the purpose of LUI. So now let us try to understand LUI using the example given in this book. So this is the number. So if what is my purpose here? My purpose here is to load this 64-bit 32-bit constant into a into this x19 register. So how to do? First, they have written LUI instruction, right? So after this LUI instruction, what will happen? So this is the LUI instruction. So LUI instruction 32 gone. So in next 32, I have to ignore this 0 to 11, 11. Then from 12 to 31, here I need to store this. So I think 0 to 11 means 1, 2, 3, 4, 8, 9, 10, 11. So up to this is actually 0 to 11 bit. Okay.
Hello, this is a correction that I am doing during the editing of the video. While I was discussing at this point, I counted the bits from 1, but actually you can see the indexes started from 0 to 11. So the bit that I am showing 11th bit, this is not the 11th bit. Actually, it is the bit number 10. If we start counting from 0, right? So 11th bit is 0. There's a one more one bit left. The bit number that I am currently showing 12 is actually bit number 11. So you have to understand this point. Remaining thing is this will be same. So that's why if you remember, I mentioned one point that if the 11th bit is 1, what you will do. So obviously in this example, the 11th bit is not 1, 11th bit is actually 0. I did a small mistake. I started counting from 1, but while I was writing, I have written it from 0. So I hope you will understand it. Then now from this point you can continue watching this video.
And from here, from this point, this is actually 12 to 31. So basically from this constant, let us make a box here. So whatever binary bits written in this box need to be stored using LUI. So this the binary written in this brown box is actually, if we want to represent this in decimal, then this will be 976. So again, I'm repeating this. The technique is, if you want to load the entire 32-bit binary constant into a register called x19, then first you use LUI instruction, and using LUI instruction, load the bit value from 12 to 31 in x19. Which position? In x19, in this position of x19. So after this instruction LUI, what will happen? So let us write it in binary so it will be clear for you. This is the x19 register. I have removed the half is here, suppose, and then these binary values will be stored here. I'm not writing the all the binary values, but 111, suppose there is this binary values which is representing 976. This will be stored here, and these values will be 0000000. Okay, and these values will be also 00000. Why? Because see, the 31 bit number 31 is 0, so all will be filled with 0. So this is the situation of x19 after LUI instruction. But this is not the complete constant, right? Because the complete constant, or you have only we have only loaded the 976 in this x19, and that too in this location. So this is not the complete constant. The complete constant has also some bit from 0 to 11. So these bits have not uploaded yet. So for this, you can use a add I instruction after this LUI. First LUI x19 976, and then you go for add I instruction x19, and this binary bit from 0 to 11. If you see 101 and this 000, this actually represents in binary, it is 1280. So if you write 1280, what you are actually doing is, these bits 1280 will be represented here, suppose, with 12 bits. Here there are 12 bits, and what will be the last bit here? Last so all bits, remaining bits will be, I think I did a mistake. uh 8, 9, 10, 11. Okay, no, it is fine. Okay, then remaining bits will be here. All will be 000, and then if you add these two value, this is, then you will get the final value. Okay, so if you want to load a constant like this type of 31-bit 32-bit constant, then first you will go with LUI, and then we'll load from 12-bit to 31-bit into the register, and then in that case the rightmost bit will be 000. Okay, and then we'll go for a add immediate instruction, and whatever bits left will add to the content of x19. In this way, you can load a 32-bit 32-bit constant in the register using these two instruction LUI and add I. But there is a problem. There is a problem, but that problem I'll discuss later. So first here, what this instruction is, this section is saying that how you can load a 32-bit constant. But the next question is how you can load a 64-bit constant. That is not given in this book. I'll also not discuss. Try to do it by yourself, that using this LUI instruction and all the instruction that you know, or that all the instructions that are discussed in this class, how can you load a 64-bit constant into a register? Because every registers are actually 64-bit of length. So technically it should accommodate a 64-bit constant, but the LUI instruction that we have shown here, the combination of LUI and add I, you can load a 32-bit instruction, 32-bit constant into the register. So how can you load a 64-bit constant? Try it yourself. But the challenge here, there is a small challenge here. The small challenge here is, when you go with LUI instruction, then LUI will load from so here, this is your LUI instruction. So LUI will load the values here, right? And then you need a add I instruction, which add I instruction will add your these values. Okay, and you are finally getting your complete 32-bit constant here. This is, you're getting the complete 32-bit constant here, right? But the problem here is, if in these 12 bits, if the 11th bit is 1, If the 11th bit is 1, it means because when we write a add I instruction x1 x2 and then we'll write a constant here, this constant is a 2's complement form, right? It can be either positive or negative, both. So if the 11th bit is 1, it means that the value is a negative value. In that case, when you are adding, suppose what when you are applying this add I, what it is happening, this is the content of register x19, and then this is the constant, right? So these two are adding. So in that case, when you are adding this constant, so this constant is only for 12 bits, but if it is a negative number, then this last bit will be 1. So this 1 will be carry forwarded here, 1 1 1 before adding. If the last bit is 0, then all this will be 0 0 0, and there will be no problem. You will get the expected value as a result. But if the last bit is 1, then all these values will be 1 1 1 1 1 before performing the addition. And in that case, you will get a different value. It is not the expected value. So because your ultimate goal of LUI and add I is to store a 32-bit constant, right? But if your the in the constant, in this 32-bit constant, if the 11th bit is 1, then it will be challenging for you. Then it will be difficult. So if you go here in this section, they have explained it, and they have also given an idea how to solve it. So I'll not explain this. Try to do it yourself, that if the 11th bit is 1, then how can you handle the problem that I have explained here? If it is not clear, then let me know. I'll explain in some other lecture. Okay, so I think how to load a instruction of a 32-bit constant is clear now. And I have given you a two tasks. First task is how to load 64-bit constant to a register, that you have to understand by yourself. And then the problem that is mentioned here, you will read and try to understand by yourself. Then let us go to the branches, addressing branches. So in last class, last two lectures, I have explained different branch instructions, branch, conditional branch instruction, unconditional branch instruction. Both instruction I've discussed. Now we'll discuss some more detail about branch instructions. So before going to branch instructions, let me show you an example of this is a program. Suppose this is a risk B program. So there are 16 instructions here. So I have written only initial three instructions. First two instructions are add instructions, and then there is a branch instruction BNE x2 comma x3, and then going to jump to L1, and this is L1. L1 is showing here. But a remaining instruction I have not written. Assume that all are there are 16 risk B instructions here. So now if there are 16 risk B instruction, we know that each instruction need how many bytes? Each instruction needs 4 bytes, right? So if I start with this, that the address of this is 0, then address of this will be 4. Suppose address is starting from 0, then this is 8, 12, right? 16, and in this way, I think the last one will be 63. This is how all the addresses you can maintain here. So I hope you are getting that. Why 0 after 0 it is 4? Because each instruction is taking 4 byte. So if it is a byte addressable memory, then the address of the first instruction will be 0, address of the second instruction will be 4, and address of the 16th instruction or last instruction will be 63. So now if we represent this in binary, then how many bits will be required? Because there are how many memories are there? There are 64 bytes are required for this program, right? Because how many instructions are there? There are 16 instructions, and each instruction is taking 4. So 16 into 4 equal to 64 bytes. So the total memory required to store this program is 64 byte. The 64 byte means 2 to the power 6 byte, right? So total 6 bit is required to represent all the addresses. So let us write the addresses here: 0 0 0 0 0 0. This is the first address. Then 0 0 1 0 0. This is the second address. Sorry, this is the second address. 0 0 1 0 0 0. This is the third address, and maybe I'll not write all the addresses. Last address will be here, I think. uh, Not 63. I think 63 will not be here. let us remove this 63 from here, that will not be here. So now after this, this 16 will be 0 uh, 0 0 1 0 0 0 0, the 16 like this. Okay, so in this way it will continue. Okay, so now let us assume that this L1, this instruction, and the number of this instruction is suppose 48. Suppose I'm assuming it is 48. So if it is 48, then suppose this is 48. So we need to write it like this. 48 means, so I need to write it as 1 1 0 0 0 0. Okay, this way. So now why I'm explaining this, so these all are addresses. These addresses are written in binary and these addresses are written in decimal. This is the program. So how many instructions are in this program? There are 16 instructions. Each instruction is taking 4 bytes. All are clear. So now what is this L1? This L1, last class also I explained, in last 2 lectures I've explained that this L1, though we are writing it as a label, but ultimately when it will be converted to machine language, this will be converted to an address of an instruction. So here, which address we will write? Instead of L1, we will write here actually 48, right? Because the instruction of L1 is, see, it is 48. So 48 will be written here in binary. So I have just written it in decimal. So instead of this L1, we will write 48. Okay, so now the question here is, in a branch instruction, if I go for a branch instruction like BNE, same instruction x2 x3 and then L1, then for this we have only 12 bits. So if we have only 12 bits, then how many unique location it can address? 0 to 2 to the power 12, right? 02 or 024096. So I means the memory location from here, the memory location, it can jump from this L1 here. Instead you can write either from any value from 0 to 4096, not more than this. So it means that at max your program must have how many instructions? At max your program must have if sorry, 2 more points I have missed. Let me explain that part, otherwise you will not understand. So if we concentrate on this particular instruction, there how many bytes are here? There are 2 to the power 2 to the power 6 bytes are here, right? So using 2 to the power 6 bytes, how many instruction you can write here? 2 to the power 6 minus 2 equal to 2 to the power 4 instructions you can write, right? And or you can say word. Why? Because each instruction is of 1 word. 1 word is also 4 byte and one instruction is also 4 byte. That this point you have to remember. If you have 2 to the power 6 bytes total in memory, then you can represent using this 2 to the power 6 bytes. How many instruction you can represent? You can represent instruction 2 to the power 6 minus 2. It is, that is 2 to the power 4 instructions you can represent. Here you can see we can represent only 16 instructions. So if this is the case, then now let us go to this 12-bit wala concept, VNE x2 x3 and then L1. Now this L1 is of 12 bits. If it is 12 bit, then as I said, you can represent from 0 to 2 to the power 12, right? With this is the maximum content. So it means that at max the memory address, the maximum memory address that you can address is 2 to the power 12. So it means that the max which means 2 to the power 10 instructions. So it means that at max 2 to the power 10 instruction is possible, not more than this. So if your BNE is limited to this only 12 bit here, means this L1 is limited with only 12 bit, then using this 12 bit, the maximum program length can, and it cannot be more than 2 to the power 10 instruction. Why? Because suppose you have a program. Let me write a program here. You have a program. This is the instruction 1, okay, and then this is instruction n. So suppose this so this is instruction number 0 and this is instruction number 2 to the power 15, suppose. And now this instruction, second instruction here, is a jump instruction, BNE x1 x2 and here suppose L1, and L1 is, this is suppose L1. So here if you want to jump from this, then the value of this L1 is more than 2 to the power 10. It is greater than 2 to the power 10, isn't it? Because you can see this first instruction is 0, and this L1 instruction is at 2 to the power, instruction number 2 to the power 15. And using this L1, you can only jump from uniquely identify instruction which is up to 2 to the power 10. So it means that the maximum length, if you want to maintain this 12 bit for a jump instruction, the maximum length of your program cannot exceed 2 to the power 10 instructions, which is a limitation here. But one more thing, there is a one interesting thing you can see here. If you see the binary pattern, why I have written the binary pattern? If you see the binary pattern, the last two bits, you can see last two bits will be always 0 0. Why last two bits will be always 0 0? Because this binary, the addresses, all each the each instruction is a 4 byte, right? So 0 4 8 12, like this. So it means that when you represent it with binary, the last two bits will be always 0 0. So if we ignore the last two bit and we can write this, so what we can write instead of this 12 bit, so suppose we have a 12-bit instruction, and then what how we can represent it. Suppose uh, suppose we have a so this suppose we have a 12, this is 12 bit. So from this 12 bit, the last two bits are always 0 0. So it means that instead of storing these two, we can store bit number 13 and bit number, so it is actually 0 to 12, right? So 0 to 11. So instead of this, we can store bit number 12 and bit number 13 also here. I hope you are understanding what I'm saying. Maybe I should repeat it. What I am trying to say, if this is 12-bit constant, since this 12-bit constant, the last two bit will be always 0 0. Okay. So if last two bit is always 0 0, it is well known. Then let us not store it here. So instead of this, we will use add two more bits here. So previously the bit was 0 to 11, that is 12 bit. Okay. Now we'll use 12, bit number 12 and 13 here, and these 12 bits will be stored here. Here this 12 bit means these 12 bit, that is bit number 0 and 1, bit number 2 to 13 will be stored here. So what the purpose here is, so whatever value we will write here in L1, suppose the value will be written here is, suppose value is 11 is 12 bits, right? So 0 0 0 4 bit, and then suppose 0 0 0, and suppose 0 1 0. If this is the constant written, so if we when computer will execute this instruction, computer will understand that okay, this constant we need to add two more zeros in the right side. So what it will do, 0 0 0 0 0 0 0 0 0 0 1 0, and two more zeros will be added, and this is your final location. This is your final location. So if we follow this concept, then what will happen? So using this 12 bit, how many unique addresses you can represent? You can represent 2 to the power 14 addresses, right? Because the rightmost two bits are always 0 0. So every time they when before calculating the final location, computer will add two more zeros in the right side. So using this 12 bit, maximum address you can is 2 to the power 14. So 2 to the power 14 means 2 to the power 12 instructions. So maximum instruction possible is 2 to the power 12 here. Okay. And I think if I go with the if I now let us go with this instruction. So they have explained BNE here. After we now one more thing that I have not explained is how to represent BNE. So this, if this is a BNE instruction x10 x11 and 2000, so how to represent this instruction? This is actually SB type instruction. I have explained you R type instruction, I type instruction, S type instruction, but I have not explained SB type instruction. So every instruction is a 32-bit instruction. There is no doubt on it. But out of this 32-bit, this are opcode, function 3. These are fixed. And if you concentrate on this instruction, it has no destination register, right? This is RS1 and this is RS2 actually. So if you see the representation, it has opcode, it has function 3, it has RS1, it has RS2. So now for this 12 bits, these here there are 12 bits. Now for this 12 bit, these part and this part remains. So basically this part is for RD, right? So here after RS2 there are 7 bits here, and between this opcode and function 3 there are 5 bits here. So using this 7 plus 5, these 12 bits we need to we will use for storing the 12 bits of this constant. So now we can that is this representation is a complex representation here. So you can see how they are storing this 12 bit. You can see out of these 12 bits they are storing bit number. So how will represent 12 bits? So normally we represent as 12. So 12 bits like this. Now if this is your 12 bit structure, then this is 0 to 11, sorry, not 12, 0 to 11 is your 12 bit structure, right? And if there is a 13 bit, then that will be 12. Yes. Okay, so now we can see how they're representing the 12 bit here. So they are saying that 1 to 4, bit number 1 to 4 will be stored here, and then bit number then 5 to 10 will be stored here, and then bit number 11 will be stored here, and bit number 12 will be stored here. Now the question is why this type of complex pattern that they are following. They are following this complex pattern because when they will design a data path of it, then this design is making the hardware easy. So I'll not explain it more detail now, because the data path will be discussed after this chapter. So at that time we will understand that how this type of distribution is making the hardware design easy. So here at this point you just need to remember the distribution, that how these 12 bits are distributed. The 12 bits are distributed like this, then 1 to 4 are in this position, and then 5 to 10 are in this position, and then 11 bit is here in this position just after opcode, and the bit number 12 bit at the extreme right left position. Okay, so now the question here is uh, if we are if we number the bit from 0, then 12 bit means 11, 0 to 11, right? So why they are using immediate 12? What is the meaning of immediate 12 here? You can see the immediate values. They are saying immediate 1 to 4. It means if this is your immediate value, now let me write a immediate value, then it will be easy for you to understand. There is a immediate value here. I'm removing everything. See, this is a 12 bit value, right? So if this is a 12 bit value, the first value here is it is bit number 0. Second value here is bit number 1, and last value here is actually bit number 11. So now try to understand how they have placed it. So since this position you need to store bit number 11, so bit number 11 is 0, they've placed 0 here. Here you need to place from 4 to 1. So 4 to 1 means 1, I think 1 0 1, then 3 0. So 1 and 3 0 they have placed here, 4 to 1. And here in this position 10 5 to 10. So 5 to 10 is all ones and followed by a 0. So this is from 5 to 10, right? And what about 12? Bit number 12. Bit number 12 is not here actually. Bit number 12 will be here, 12. So they are storing bit number 12 also here. So now now the question is why they are not storing 0? Why bit number 0? So that part I've explained here, right? If you see here, then the first two bits are actually not required, so you can ignore the first 2 bit. Now the next question is why they are ignoring only 1 bit, why not 2 bit? If I follow the policy that I'm explaining here, that first 2 bits are not required, then that should start storing from bit number 2, right? Not from bit number 1. So why is the problem? There is no problem. Only thing is they assume that since currently the number of bits here are 32, the number of bits required to represent one instruction is 32 bits. So they assume that in future when they've written this book, they assume that in future maybe a 16-bit representation of risk B may also come. So the way they have designed all this format, in such a way that it should work for both 32-bit instruction as well as 16-bit instructions. But that's it. Remaining thing written in this book is for 32-bit instructions only. So but since they assume that in future maybe it should fit on it can fit a 16-bit instruction also, so that's why they ignored only 1 bit, not 2 bit. because if instead of 32 bit, if it is for 16 bit, then only one bit in the rightmost side will be useless. Okay, that's why they ignore only one bit, but technically we can leave 2 bits. Okay, so now let us again go with this 12 bit wala. If we have only 12 bits, then if I go with this policy that I'm saying, that I said, then we have 2 to the power 14 bits. So with this 2 to the power 14, how many instruction we can represent? 0 to 2 to the power 12 instruction we can represent, right? But if we go for the format that I have given here, so here what they are saying, maximum is 2 to the power 13, not 14, right? So they are storing 0 to 12 bits here. See, 0 to 12 bits, so it is 13. So 2 to the power 13 means 0 to how many instruction you can store? 0 to 2 to the power 11 instructions you can, maximum instruction you can store. So we'll not go with this design that I've explained, that 2 bits wala design will not go. We'll go with that only 1 bit is not required in the right side. Why? Because to maintain uniformity with the book. So if we maintain uniformity with the book, we'll remove this line and we'll go with this line, that there are 13 bits, though we are using 12 bits here. If there is a BNE instruction in this instruction, though there are 12 bits here, but this two, using this 12 bit, you can represent 13 bit, because if we add a 0 at the rightmost position, then this 12 bit will become a 13 bit. So using this 13 bit, how many instruction you can represent? Maximum instruction you can represent, how many instruction you can represent? 2 to the power 11. Okay, but still there is a limitation, right? 2 to the power 11 means if we can only write a program where maximum instruction size should be 2 to the power 11, not more than that. That is still a limitation. But I hope whatever I've explained here is clear to you. And then let us go to next instruction, that is a gel instruction. If I go to, I think gel also I have explained in last class, the recorded lecture that I have loaded on Friday. In that lecture, the gel is explained properly. So gel is an unconditional jump, right? Gel x0 and then suppose 2000. So this is the location where the instructional jump. This is the unconditional jump. So if you concentrate on this instruction, then this instruction only has a RD. This is the destination register. Okay. So I'll not explain the detail here, because if you want to understand the detail of gel, then please watch my previous lecture where I've explained the purpose of gel. Here, this is a destination register and this is the level, or you can say immediate value. So for this immediate value in gel, we have 20 bits, not 12 bits. In conditional jump, we have only 12 bits to represent the immediate field. Here we have 20 bits. So using this 20 bits, how many addresses we can count? If we follow the same concept here, that last bit is not required, then we have 21 bits. This 20 bit actually 21 bits, right? Because we can add 10 at the rightmost position. So it means that the maximum number of instructions that we can represent with 20 total is, if this is the, if 2 to the power 20 bytes we can represent, right? And using this, we can, maximum instruction is 2 to the power 19. So 2 to the power 19 instructions, sorry, 2 to the power 19 instructions or words you can represent. So I hope it is clear. In case of BNE, if we go with BNE, then maximum instruction possible is 2 to the power 11. If we go with ZEL, then maximum instruction possible is 2 to the power 19. And I think if we this is the format of a representation of gel. Gel is a UJ type instruction. The BNE and all conditional branch instructions are of SB type, that I have already said. These are SB type instructions. Please remember this, SB type instruction. But this gel is a UJ type instruction, so its format is also different. So here also again, this is a 32-bit instruction. First part is opcode, and after opcode, the remaining, even this function, this representation has no function 3 also. So after opcode, there is a field for RD. As I said, gel has a RD. You can see gel has a RD. So the destination register will be filled here, and then all the remaining 20 bits here is for the immediate part. But these 20 bits are also distributed. You can see how they have written it. 1 to 10 here, this location, then 11 here in this location, and then 12 to 19 here just after the destination register, and the last bit, immediate bit, is 20 is here at the end. Why again this type of complex distribution? Because this type of complex distribution is helping to design a better hardware, and that we will discuss in chapter in this next chapter. So at this moment you have to remember the bit distribution of both the structure, this and this is important. You should remember the bit distribution. Okay, so now I'm not explaining this in detail, but what you can do is, see, you can concentrate on this gel instruction and you can concentrate this value. So this value is can be represented as binary with this value. So now try to understand how this value is plotted here in this box. Try to understand it. Okay, so I think BNE is clear. BNE is SP type instruction, or all the conditional jump instruction, not just BNE, all are SP type instruction, and how to represent them, that I have explained. Then I've explained you a conditional, unconditional jump like gel, and these in gel, how to represent these are user type instruction, that I've also discussed, right? And then I've also discussed the limitation that for all the conditional instruction like BNE, that this the 12 bits that is required available for immediate, how many instruction you can if possible with 12 bits, maximum instruction possible is 2 to the power 11 in a program. So not more than that. If the program has more instruction, more than 2 to the power 11 instruction, then this type of branch instruction cannot be used. Okay, and if it is a gel instruction, then in case of gel instruction, your program total instruction in your program should not exceed 2 to the power 19, otherwise there will be a problem. Okay, so all these things I have explained till this point. Now the next question is it practical? Is it practical that we should limit the number of instruction to 2 to the power 19? In modern applications, when we will write a software, the normally all the software, all the programs that we write, sometimes it has millions of lines of coding, right? So in normal scenario, in modern day, it is not practical to limit that. Okay, every program will have only a number of instruction will be limited to 2 to the power 19. This is not at all a practical solution. So what is the alternative? So alternative is the L1 that I am writing here, this L1 concentrator, this L1. What I say till now, I said this L1 is a address of instruction, right? I said whatever the 48 I have written, this is 48 is a address of this L1 instruction, right? So now at this point I'll change it. I'll not say that from no, this is not an address. Let us write it a displacement. Means I'll fix a particular register. I'll say the L1 means from here how many byte, means suppose register is X, so X plus how many byte, suppose X plus 12 bytes. So this 12 will be written in L1. So this is L1. So go to X plus 12, go to X plus 13, go to X plus 14, like this. So normally what is this X? Normally this X is actually program counter. This register is called program counter. So whenever we write here BNE x2 comma x3 comma L1, then where it will jump, normally it jumps to program counter plus L1. So from program counter, either it will go this direction or this direction. Okay, so let us consider upper direction means plus side, or lower direction means minus side. So both direction it can go. So now the question is how much distance it can travel from program counter. So again, these 12 bits are there in L1, right? L1 has 12 bits that I have explained. I'm only concentrating on BNE, but this 12 bit is ultimately 13 bits, right? That also I've explained. The 12 bits is actually 13 bits. So you have 13 bits. So from this 13 bit, one bit is required for up and down, right? The upper side or lower side, and remaining 12 bits you can represent to you can use to represent a byte. So 2 to the power 12 you can use to represent a byte, means go to 16 byte up, go 16 byte down, you can represent this. Okay, so using this 2 to the power 12, how many instruction you can represent? You can represent instructions 2 less, right? So 2 to the power 12, sorry, plus minus 2 to the power 12 minus 2 equal to plus minus 2 to the power 10. So if we go with PC relative addressing, PC relative addressing means this L1 is actually PC plus L1. If we go to this, then in that case, if suppose this is your BNE instruction, BNE x1 x2 L1, then in this side you can represent 2 to the power 10 instruction. In this side also you can go till 2 to the power 10 instruction. So this is now the limitation is extended. Previously what I was saying that every time this L1 will only if this L1 is representing a address of instruction, then only 2 to the power 11 number of instruction is possible in a program, but that is not possible, that is not restricted here. Here we are saying that for any location of L1 it can jump either 2 to the power 10 up or 2 to the power 10 down. I hope it is clear that why 2 to the power 10 up and 2 to the power 10 down. I'm again explaining this part because there are 13 bits, right? 12 bits is actually 13 bit, that I've already explained. So there are 13 bits. So out of the 13 bits, one bit will be required for up and down, and then remaining 12 bits you can represent as byte. So here in PC addressing, L1 means PC plus the how many bytes. This here if I write 48, then PC plus 48 bytes. Okay. So out of this 2 to the power 12 bytes, how many instruction you can represent? Plus minus 2 to the power 10. That's why I said 2 to the power 10 instruction up, 2 to the power 10 instruction down. So now this previous limitation is extended. So the same concept if I apply on gel. So gel has how many gel x1, and then this immediate value in gel is 20 bits, right? So 20 bits means 21 bits. And with 21 bits, so plus minus 1 bit is required for up and down, then 2 to the power 20 bytes it can represent. So out of this 2 to the power 21 bytes, how many instruction? 2 to the power 18 instruction up and 2 to the power 18 instruction down it can go. So now the limitation is removed. All the solution that I have given, it's I think it will work for almost all the application, because if you write this sentence here, it is written spec benchmarks for means about half of all the conditional branches in spec benchmark go to location less than 16 instruction away. What is spec benchmark? I think I have explained once that spec benchmark is a standard set of application that we normally use to measure the performance of a computer. So it is a standard set of applications. So it has been found that in all the applications available in this spec benchmarks, it has been found that when we jump from one instruction to another, the destination address is within the 16 instruction away. So if this is the case, then I think if we go with PC relative addressing, that PC plus L1, then the problem that I discussed previously, that problem is resolved here. If any point is not clear, then you can what you do, you can watch my lecture again, and after that you read the book. Even after reading the book, if any point is not clear, then you can send me email. I'll clear your doubts. Okay, so I hope the PC related addressing concept is clear. Now there is one more problem. One more problem is the jumping instructions. The problem of jumping instruction. Jumping instruction means conditional jump or unconditional jump is resolved with PC related addressing. But there are one more problem. One more problem is when we'll call the function. When we'll call a function, that time it may be possible that suppose this is this is BNE, right? Instead of BNE, if I write here a gel instruction, then here it is 2 to the power 20, 2 to the power 20, that I've explained, right? Maybe from this point you need to jump a point here. You need to jump a point here. Okay, and which is outside. It is more than 2 to the power 20 below the below the jump instruction here written. Okay, so this type of jump is possible when we are calling a procedure. So what to do in that case? The PC related addressing solution is also not applicable. So this part they have explained, I think, here. If you read this part, they have explained it here, and they say that how you can directly write a 32-bit instruction here. Means gel any jump instruction, suppose x1 instead of x1, and here suppose in this location, normally in this location you can instead of this location you can use a 32-bit address. How? Directly you cannot use 32-bit address here because you don't have space here, right? You don't have space to represent 32-bit. It makes your space here for 20 bits. So how can you represent a 32-bit? For this they have used the concept of LUI. So suppose you have a 32-bit address, okay, and you want to jump your program to this location. So 0 to 11 and then 12 to 31. So this 12 to 13 you can load in a register using LUI. Suppose in X19 register you will load using LUI, and after that you will use JLR X19, And suppose this constant is suppose 1028, then I will write 1028 in bracket, sorry, here I'll write x1, and in bracket I'll write x19. So in this way you can jump. So this concept is explained here. Try to understand it. If this point is not clear, then let me know why I'm not explaining it in detail, because I've already explained you LUI. Only thing you need to understand here is JLAR. JLAR, it's not PC related addressing, it's a register related addressing. How it will jump? It will jump to this address, the content of this register plus this. So if you add these two, then it's a 32-bit address that I was trying to add here. Okay, so I think let me repeat whatever I have explained. I'm not showing you this. I'm not explaining you this example. Why? Because I've explained you an example here. The example is almost similar. Try to understand the example that is given in this book. Try to understand this. If you understand the example that that I've shown here, then in the right side, then you will also understand the example that is shown in the left side, that is in the book. Okay, so if I scroll down here, this is a very interesting concept written here. So here, if you concentrate on this BEQ, so here the maximum distance what it can jump, PC minus 2 to the power 10 or PC plus minus 2 to the power 10, right? That I have already explained that you can jump. What about if it's want to jump more? Suppose in this position, suppose this is 2 to the power 10 and here it is 2 to the power 10, and using this I want to jump from this location to this location, which is outside to the pattern. How can you do this? It may be possible, isn't it? So if when we discuss about gel, then there are this is PC plus 2 to the power 20. I said this can solve all the problem, but when we discuss about BEQ, here it is PC plus 2 to the power 10. So this sometimes may create problem. This sometimes may create problem, and problem is here if you want to jump in this location. So you can solve this problem easily if you convert this single line code into this 3-line code. I'll not explain it. Try to understand it by yourself. If we convert this single line code that is written above, if we convert this single line code into this 3 lines code, then ultimately the meaning is same, but you will resolve the problem. And here now in this case, you can go with PC plus minus 2 to the power 20. Try to understand what is how. It is your responsibility to understand this example. So if I quickly scroll down what I've explained today, I first explain that how you can load a 32-bit constant into a register using LUI and ADI. And I said that you also check how you can load a 64-bit constant using LUI and any other instruction that I have discussed in class. And also I said if in LUI the bit number 11 is 1, then how to handle the problem. That also you need to understand by yourself. Then I explain the 2-type branching instruction, SB type branching instruction, where only 12 bits are there to represent a location. And then I explain you user type instructions, that is gel, so where 20 bits are there to represent the instructions, and their limitations and how to overcome the limitation using PC based addressing, PC relative addressing, PC relative addressing. Okay, after that I explained that sometime when you will call a function, then PC relative addressing may not be enough. In that case you need LUI and JLR, combination of LUI and JLR, that you need to understand by yourself, that I've explained. And then I told you that you need to understand this program by yourself. After that there is an interesting example. That example also you need to understand, by yourself, because all the concept required to understand this program is explained in class. There are only two small things are required here. The RISC-V instruction that we have explained till now in this class, they can be divided into 4 addressing mode: immediate addressing mode, register addressing mode, base or displacement addressing mode, and PC relative addressing. So let us try to understand quickly. Immediate addressing mode means there is example will be add x1, x2, 25. This is the immediate addressing mode. Here only opcode, RD, function 3, RS1, and I is required. This I type instruction. These are your I type instructions. Okay, then register addressing means example is add x1, x2, x3. This is a register addressing mode or R type instructions. Okay, base addressing mode, these instructions are JLR. So the instruction that I have explained now, just few minutes before, 2 to the power x19. Suppose this is a base address instruction, means we'll go to a location, we'll jump to a location after adding immediate with a base register. Okay, this is the base register x19. We'll add a constant with base register, or add a immediate with base register, and then we'll jump. So these are called base addressing instructions, or addressing. And then PC relative addressing, all the jump instruction, BNE instruction, JAL instruction, these are PC relative addressing, right? So these are the four addressing mode in RISC-V. You have to remember those, and you have to also remember some examples. For example, immediate addressing means add I, and I, all are immediate addressing. Then register addressing, add, subtract, all R type instructions are register addressing. Base addressing, one instruction is JLR. And PC relative, some examples are BNE, BEQ, GEL, all are PC relative addressing. So I'll stop here. And one more thing here, decode a machine language. Decode a machine. Suppose you have a 32-bit instruction given like this. How can you convert it to a assembly language instruction? Try it by yourself. I explain you all the representation of I type, R type, SB type, user type, right? So based on all, try to understand how to represent this binary into a particular assembly language instruction. And for this you need a table where the opcode function 3 and function 7 are represented. This table is here. I think in the from the beginning I was saying that you will find a table at the end of this chapter. This table is here. If you see the table here, for R type, the distribution of opcode function 3 and function 7, I type, S type, SB type, U type, user type, all are explained here. So if you know this table, then based on this table you can easily convert this instruction, this 32-bit to a RISC-V instruction. But you no need to remember this table. This table will be supplied to you in every exam, so you no need to remember, but just you need to know that how to convert. If you know, if this table is available, then how to convert a 32-bit binary values into a RISC-V instruction, that you should know. Okay, so I'll stop here, and next class I'll start from a new section. I've not checked any comment. Let me see comments. So there are a lot of questions. Somehow I ignored. These instructions are fetched from RAM or stored in some other location, because in case of RAM, the address of instruction need not start from zero. So the address of instruction need not start from zero. I just shown you here. I've just give you an example. It may not start with zero, right? The instructions are fetched from RAM or stored in some other location. Normally instructions are the address that I'm right that will write here. This address are actually from main memory. These are from RAM, and it is need not start from zero. It's also true if because some addresses will be reserved for operating system, and as a normal user you cannot use all the addresses. But as a simplified model, here I assume that the addresses are starting from the instructions are fetched from RAM. This is true, but as a simplified model, here I assume that addresses are starting from zero and you have access of all the RAM. That I am assumed here. Any other doubts? I think I'm already late. It is already 3, so I'll stop here. And if you have any doubt, you can send me email.